The Event Horizon Telescope collaboration have done it. They've produced the first ever direct image of Sagittarius A star, the supermassive black hole at the center of our home galaxy. Sag A star is the Milky Way's ultimate dark star. Its light crashes and pours itself out into ashes of gas and plasma that surround the black hole, traveling nearly at the speed of light. It is absolutely an astonishing achievement. And yes, I know that this news came out a little while ago, but on that very same day, I threw out my back, and I'm still wearing a support belt and doing physical therapy, but I'm finally feeling well enough to at least talk about this, and to tell you the truth, it's no less exciting because now that the initial announcement has passed, we can start to dig into some of the technical details and especially the astrophysics. And there's an awful lot to unpack because there are something like 6 major papers as well as 4 supplementary papers that really almost entirely deserve videos of their own. But we'll just go ahead and summarize some of the main points here. The first thing I can't help but notice is just how similar Sag A star appears to the first image of a supermassive black hole in the galaxy M87. The colors are the same, but let's remember that they're just representations of the radio signals. By all rights, these images should be grayscale, but the orange colors help to evaluate the differences in brightness and contrast. And this is the same technique that was used to evaluate the James Webb Space Telescope's engineering images. Both images show an elongated ring of emission surrounding an inner dark region. Now, this is light that's coming from a disk of extremely hot gas surrounding the black hole. At the center isn't so much the black hole itself, but rather its shadow. And that's because light rays get slingshot around the black hole. So any light rays that escape and reach our telescope are leaving a shadow where the black hole actually is. Inside the shadow is the black hole itself, the point of no return to our universe. And yes, it looks like a blurry donut. But believe it or not, this is actually one of the sharpest images ever created. This tiny ring of light has an angular size of just 51.8 micro arcseconds across. That's 0.0000518 of an arcsecond, or if you prefer, 0.00000000144 of a degree. But to give you an idea of just how insanely tiny this is, the full moon is about half a degree, or 30 arc minutes, or 1,800 arcseconds across. But Sagittarius A star's image is about the same angular size as a donut lying on the moon's surface. So the donuts appear blurry because we're looking right down to the very limit of a telescope that's the size of Earth. Now, obviously, no such telescope exists. And that's why the Event Horizon Telescope, or EHT, is a virtual computational telescope. It works by linking together several existing radio telescopes around the planet to act in unison as a single Earth-sized telescope. And this technique is called Very Long Baseline Interferometry, or VLBI. It's the same technique that was used to image M87 star. However, Sagittarius A star's location in the sky allowed the South Pole Telescope to be used for the first time, bringing the array to 8 telescopes in total. The South Pole Telescope has a continuous view of Sagittarius A star, so that makes the array larger and more sensitive. And that's important because VLBI depends on having as many pairs of telescopes as possible. Each pair produces a baseline that produces a data point of information. It's like shaking hands with 7 other people at the beginning of a meeting. Everyone shakes hands with one other person at a time. The more people, the more handshakes. The more handshakes, the more information gets passed around. And EHT generated a lot of information. During its 2017 campaign, its 8 telescopes produced about 3.5 petabytes of data of Sagittarius A star alone. That's 3,000 terabytes. It would literally take years to download that much data over the internet. So that's why specialized high-speed hard drive recorders were installed at each telescope. The recorders used atomic clocks to timestamp the data precisely to ensure that they could be synchronized later. Then the disk packs were shipped to a pair of supercomputers called correlators, located in Massachusetts and Germany. But even then, they had to wait a few more months for all of the data to arrive because when the data was taken in April of 2017, flights in and out from the South Pole had already shut down for the winter, so they couldn't even fly the data out until after the sun returned later that year. But once the data were finally loaded into the correlators, the signals from the telescopes could be combined to produce an image. Each pair of telescopes contributes information in different ways. Pairs that are far apart resolve the smallest features and produce the sharpest parts of the image. Pairs at different orientations pick up different parts of the image. With enough orientations, you could, in principle, recover all of the sharpest features of the image. Telescopes that are closer together don't have quite as good resolution, but they can pick up broader features that the widely separated pairs miss. Making a perfect image would require telescopes placed everywhere to capture every possible combination of separations and orientations. EHT only had 8 telescopes for Sagittarius A star. Fortunately, however, Earth's rotation allowed the telescopes to fill in some more of the missing pieces of the picture. The more observations, the more data was generated, and the more of the image could be created. It's like building up an image by adding more pieces to a virtual mirror over time. But even then, we're still left with fragments of the image. The rest still has to be reconstructed from the available data. But how do you fill in the rest of the image when there's no image there? Well, to understand the basic idea, let's imagine that we're looking at different parts of an image of something, and we're trying to figure out what it is. As we look at the different fragments, we can start to recognize things like the red color, the texture of the skin, and so on. If we look long enough, our brains start to fill in the rest, and we realize we're looking at an apple. This technique works well when the target is sitting still as EHT observes it for several hours at a time. But Sagittarius A star really wasn't posing for its picture. Instead, it was rather jumpy. To understand why, we need to understand the nature of these two black holes. M87 star is a mammoth at 6.5 billion solar masses. It's surrounded by a large accretion disk and powers an enormous relativistic jet. It's not at all typical of a black hole. In fact, it's a supermassive black hole's supermassive black hole. On the other hand, Sagittarius A star is actually very common. It's at the center of a smaller spiral galaxy. It's only 4 million solar masses, and it's accreting much less matter. In other words, pretty typical of supermassive black holes in most galaxies. M87's shadow alone is several times larger than our entire solar system, while the entirety of Sagittarius A star's surrounding ring could fit inside the orbit of Mercury. But M87 is 55 million light-years away, so even though it's 1,500 times larger than Sagittarius A star, it's also 1,500 times further. So both objects appear to have about the same angular size on the sky. But Sag A star's small size makes for a very dynamic and very turbulent environment. Both black holes are surrounded by rings of gas that are both orbiting at roughly the speed of light. However, M87's gas takes several days to weeks to complete a single orbit, while Sagittarius A star's gas takes just a few minutes. So over an 8 to 10 hour observation period, the ring is actively changing and bits and pieces of it are constantly moving around. Not only that, but in order to see Sagittarius A star, we have to look through the galactic disk. If you look out in the Milky Way, you see all kinds of dark lanes of dust, and that prevents all of the visible light from getting through. To have any chance of seeing it at all, you have to go to longer wavelengths such as infrared or radio. But even then, some of the radio light gets scattered as well. M87's black hole lies at the center of a large elliptical galaxy with relatively little gas and dust blocking our view. It's even located far above the plane of the Milky Way, making it relatively easy to see. It's really like the difference between trying to photograph a large dog that's sitting still versus a puppy that's chasing its tail as viewed through a rainy window. So how do they deal with all of this variability? Well, after the data was initially correlated, they were sent to independent teams for imaging. Each team used different algorithms and adjusted different parameters to come up with a library of possible images that could then be compared to one another. When the imaging teams were complete, they had a library of tens of thousands of different possible images that were reconstructed slightly differently, but all were consistent with the input data from the telescopes. But with tens of thousands of images to choose from, the team then switched to clustering the images according to certain characteristics. 3 of the clusters showed a clear ring with different blobs of brightness at different intensities and slightly different orientations. A smaller fourth cluster didn't appear ring-like at all, but they couldn't completely rule them out either because it's not clear exactly what this was supposed to look like. So the teams took a weighted average and combined them to produce the image that we see here. And this is why it took 3 more years of imaging tests on real and simulated data to really build up the confidence that what we're seeing in this image is real and not something wrong with the software or some systematic bias in the algorithms that produce the image. But what exactly are we looking at? Well, in M87's case, it's fair to say that the image is real in the sense that there's a large ring of light that shows up in virtually every possible image reconstruction. All of the reconstructed images have similar orientations and features, and most of the reconstructions show that the bottom part of the ring is brighter than the upper part. And this is consistent with a phenomenon called Doppler beaming or relativistic boosting. And the idea is pretty simple. If the disk were exactly flat on to our line of sight, then we would expect the light from the disk to be roughly equal brightness. However, if the disk were tilted slightly and rotating, then we would expect to see that this part of the disk is actually approaching us while this part of the disk is moving away from us. The part of the disk that approaches us gets a boost. The light adds up in a way as to make this part of the disk brighter, while this part of the disk is moving away and therefore gets some energy weakening and therefore appears to be a little fainter. That's all well and good for M87, but Sagittarius A*'s image is a little bit harder to characterize. I mean, yes, there is a ring of the same angular size as M87, and that's consistent with the difference in physical sizes and their distances. More importantly, it's also consistent with what general relativity predicts. So in order to understand what the image is telling us, the teams then started to build models and test them against the actual image. For example, we can begin by approximating the image using a simple model of an ordinary ring. We can then start to change different parameters like its size and maybe its thickness and figure out if we're looking at a thin or thicker and more diffuse ring. We can also adjust parameters such as its orientation, its elongation, and even brightness around the ring. Now already our model starts to look very similar to the actual image. But Sagittarius A* is dynamic and changing rapidly, so how do you fit the data to all of that variability? Well, the good news is that we already know the mass of Sag A* from stellar orbits, and that allows 2 different modeling approaches to be used. The first is called snapshot modeling. On timescales of about 2 minutes, the structure at Sag A* should remain relatively still, so individual fits can be generated to these small time chunks like frames of a movie. These are later combined into a single average model. The other technique is to model all of the data at once in what's called full stack modeling, and this fits for the average of all of the time signatures plus the noise. And this is similar to how the images were actually created by EHT in the first place. Both techniques were used over and over again with different combinations of parameters. In the end, they generated more than 5 million possible fits, all with different combinations of angles, ring sizes, spins, magnetic fields, and so on. That's a lot of possible solutions to the data, so each one had to be tested in order to see how well they matched the actual dataset. Any results that had too much diffuse emission and appeared too large on the sky were rejected. Anything that had a ring that looked different in shape from the EHT image were also taken out as well. Some results included too much light at other frequencies that were not actually part of the EHT image, and others showed evidence of outflows that just were not seen at longer wavelengths. That leaves just 2 models that fit most, but not all, of the EHT data. Both models require very small amounts of accretion. To give you an idea of just how small this is, if Sagittarius A*'s mass were scaled to a human, that human would eat only 1 grain of rice every 1 million years. Not only that, but it's actually producing very low emission for the little amount of matter it's eating. Just 1 part in 1,000th of the gravitational energy of the mass falling into the black hole gets converted into light. As a result, Sag A*'s ring is only about 100 times the luminosity of our sun. We could never see this in another galaxy. even though it's the most common type of supermassive black hole. The models also require that the orientation of the ring has to be pretty close to face-on. So what that means is that if the rings were seen face-on, they would be at 0 degrees inclination, whereas if the ring was seen edge-on, that would be 90 degrees inclination. So at less than 50 degrees, we're probably are looking at an orientation maybe kind of like this. Not exactly face-on, but definitely nowhere near the edge-on case either. Now that's interesting because that means that the spin axis of the black hole is actually aimed at us and is not aligned with the plane of the galaxy. Now that's surprising, at least to me, because I would have assumed that the black hole was spinning in the same direction as the rest of the galaxy. But it turns out that's really not entirely unexpected either. You see, the Milky Way was built up by consuming smaller galaxies. In fact, it's still doing that right now. Each of those smaller galaxies presumably have their own intermediate mass black holes, which have their own spin, so the merging black hole spin would have to be different from the original. So it's quite possible that our Milky Way's black hole once upon a time was spinning with the rest of the galaxy, but mergers with other objects gradually changed its spin direction over time. However, the remaining models don't explain every remaining aspect of the EHT image, especially those 3 blobs. Now, blobs like these are not unexpected because theory predicts that there should be regions of greater magnetic intensity and other general relativistic magneto-hydrodynamic phenomena. However, the exact orientation and intensity of the blobs in the best fit models are still not exactly lined up with what we see in the EHT images. And these blobs tended to line up in directions where they had more telescopes laid out on the ground. So they could be in part imaging artifacts. And there's also the fact that this is a very rapidly changing environment producing a necessarily blurred image. So in order to really understand what's going on in Sgr A star, the EHT team would like to now go back and get more images with more data over more observations over different timescales. So far, they've done this with observing runs in 2018, 2019, 2021, and just recently in 2022. Not only that, but more telescopes have been added since the 2017 run, and EHT now has a total of 11 operational telescopes at its disposal. So with more of these observations under analysis, the teams hope to generate movies of Sagittarius A star. Another thing that would be great would be to improve the resolution. The next generation Event Horizon telescope will go to 345 gigahertz, and that will cut down the scattering and noise in half. And then there's just adding more colors, so to speak. Remember, these are monochromatic images taken at largely one frequency. The EHT team is going to go back and image with more frequencies to effectively add more colors to the palette and really try to understand the different physical characteristics of the ring and try to build up a better image of the black hole at the center of our galaxy. The coming years are going to be amazing, and it's going to take some of the best and most brilliant minds to help us to make sense of the petabytes upon petabytes of data that we are pulling down from these telescopes. And that's why I'm so thankful to have Brilliant for sponsoring today's video. Brilliant is an amazing tool for learning STEM interactively. For example, understanding how polarization works, the dynamics of fluids and gases, and how computer algorithms can be used to solve complex puzzles are essential to imaging black holes. Interactive learning is the best way to not just play around with ideas, but to really understand them at a deeper level. Brilliant's platform is enjoyed by thousands of users around the globe and allows you to learn at your own pace. You can learn on the go and always learn something new, even just as a matter of fun. And to get started for free, you can visit brilliant.org/launchpadastronomy or click on the link in the description of this video. The first 200 visitors to this link will get 20% off of Brilliant's annual premium subscription. My thanks as always to my Patreon supporters who are helping to keep Launchpad Astronomy going, and I'd like to welcome Gear Bildoy, Paul Larkin, and Joshua Stallworth as my newest supporters. And if you'd like to join me on this journey through this amazing universe of ours, well, please make sure you subscribe and ring that notification bell so that you don't miss out on any new videos. Until next time, stay curious, my friend.